good morning. Let's start with the assignment 5, contour integration using the Jordan's lemma. This integration I need to prove. That is from 0 to infinity integration cos of mx over x to the power 4 plus a to the power 4 dx is equal to pi over 2a cube e to the power minus ma by root 2 sine of ma by root 2 minus pi by 4, where m is strictly positive. Whenever you are having cosine or sine in the numerator, just remember that we need to change the numerator in e to the power iota mz, right? So that I can apply the Euler's formula later and write the denominator as it is in terms of z, right? From here you will start the integration. And now then after that, after proving this result, I have to deduce that integration from 0 to infinity x sine of mx over x to the power 4 plus a to the power 4 dx is equal to pi over 2a square e to the power minus ma by root 2 sine of ma by root 2. If you look here carefully, this is nothing but the differentiation of the above result with respect to m. If you differentiate this result with respect to m on both the sides, you will get this final result, right? So let's start with the solution. Alright, as I have said earlier that I have to integrate f of z to be equal to, because I am having cos of mx in the numerator, I have to write the numerator as e to the power iota mz, right? And in the denominator it's same, just z to the power 4 plus a to the power 4. Replace x with z. So we will integrate f of z, right? Alright. We will integrate this f of z along c, where c is your contour consisting of the real axis from negative r to positive r, followed by a semicircle tau from positive r to negative r in the upper half plane, right? So the first step is to find out the poles. So how to find the poles? Just take the denominator equal to 0 and find the value of z. The points which are just that points are the poles. Now for that, just put first denominator equal to 0. Z to the power 4 plus a to the power 4 is equal to 0. Then this z to the power 4 is equal to negative of a to the power 4. And I know that this negative 1, this is nothing but e raised to the power 2k plus 1 pi iota. This I have already explained in the previous video, where this k is from 0, 1, 2, 3. That's it. Why up to 3? Because I'm having the power 4 here, right? Now what are the poles now? Put k equal to 0 first. Here I will get a to the power 4 e raised to the power pi iota. Alright, first you have to get the value of z. Z is equal to a e raised to the power 2k plus 1 pi iota over 4, right? Now put here k is equal to 0 first, and then k is equal to 1, and then k is equal to 2 and 3. You will get 4 simple poles. For k equal to 0, I am getting a e raised to the power pi iota by 4. And then put k equal to 1, I will get a e raised to the power 3 pi iota by 4. And for k is equal to 2, I get a e to the power 5 pi iota by 4. And then for k is equal to 3, I get a e to the power pi 7 pi iota by 4, right? This is 7 pi iota by 4. So I got my 4 simple poles at these points, right? Now the question arises, which of the poles lies inside the contour? So whatever number of poles you are getting, first half poles lie inside the contour. Suppose I'm having 2n number of poles, then first n poles lie inside the contour. I'm having number of poles here 4. So first 2 poles lie inside the contour. Now the second step is to find the residue of Fz at these 2 poles, right? Let me consider these 2 poles, the one of the poles to be as z equal to alpha. Let's suppose that at z equal to alpha, let's calculate the residue. And then we will put the value of these 2 poles and then add the residues, right? Okay. Now what is the residue of Fz at z equal to alpha? There is a formula, that is e the power iota mz. Write whatever there in the numerator. I'm having e the power iota mz in the numerator, and then derivate the denominator with respect to z. Okay, so derivate the denominator with respect to z. At z is equal to alpha. Now in the numerator I'm having e the power iota mz, putting z equal to alpha, so I get e the power iota m alpha over. Now the derivative is 4z cube, so also put the value of z here, so 4 alpha cube. This is the residue. Okay. Now to calculate the sum of the residues at these 2 poles, first put a e the power pi iota by 4 here in place of alpha, and then put this second pole and then add these 2 residues. So the sum of the residue of Fz at these 2 poles, that is equal to, I'm just writing 1 by 4 e the power iota ma. This is, I'm putting the value of first e the power pi iota by 4 first, this thing, over 4 alpha cube. 4 is already outside, so alpha cube. Alpha cube is a cube e the power 3 pi iota by 4. So this is a cube e the power 3 pi iota by 4 plus second e the power iota m. What is alpha now? This is a e the power 3 pi iota by 4. A e the power 3 pi iota by 4 over a cube. So this is a cube e the power, yes, 9 pi iota by 4 exactly. Now I need to make some of the adjustments over here, because I'm having a sine of ma over root 2 minus pi by 4. So I need the angle to be in ma by root 2 minus pi by 4. I require pi by 4 everywhere, or ma by root 2 I need. So because I need to finally apply the Euler's formula last. So this is 1 by 4 e the power iota ma. I'm having e the power pi iota by 4. Now if you apply the Euler's formula over here, this is cos of pi by 4 plus iota sine of pi by 4. So just I'm writing here, it is 1 plus iota over root 2, right? In all, I just write here. So this is a cube. What is e 3 pi by 4? Instead of this, can I write e the power, okay, instead of 3 pi iota, I'm using 4 pi iota minus pi iota by 4, because I need pi by 4, something like that, plus e the power iota ma. Now here I'm not using the Euler formula. Again I'm using here e the power pi iota by 2 e the power pi iota by 4. If you add these two, you will get back your 3 pi iota by 4 over a cube. Now instead of 9 pi iota, can I write 8 pi iota minus pi iota? So this is 8 pi iota minus pi iota, so that I can get again pi by 4. Alright, now when you multiply this iota inside, you will get e the power minus ma over root 2 into e the power iota ma over root 2 upon, I'm taking this a cube outside, okay, so this is e the power pi iota. If you take this 4 inside, so this is e the power pi iota, right? And this is e the power negative pi iota by 4 plus this is e the power iota ma, and this is, okay, e the power pi iota by 2. What is this? Just use the Euler formula, cos of pi by 2 plus iota sine of pi by 2. So from here you get iota, and e the power pi iota by 4 is again cos pi by 4 plus iota sine pi by 4, which is again 1 plus iota over root 2. Fine. And here just take 4 inside, you get e the power 2 pi iota and e the power pi iota over 4, right? Okay, now again this is 1 over 4 a cube. If I solve this, what I get, okay, just look in the denominator, this is e the power pi iota. What is this? This is negative of 1, right? So can I just write negative over here? And what is e the power 2 pi iota? It is cos of 2 pi plus iota sine of 2 pi. Cos of 2 pi is 1, so this is nothing but just 1. Right? Okay. Now when you take this in the numerator, you will get e the power iota ma over root 2 plus pi by 4, and with negative value, because if you multiply these two, you will get something negative here, e the power minus iota ma over root 2 plus pi by 4. Right, just take this e the power pi iota by 4 in the numerator, you get this. Now why I'm having negative sign over here? Because I'm taking this negative outside and then I will get negative inside, and of course there is one more constant from the numerator which is coming commonly outside, that is e the power minus ma over root 2. This thing, e the power minus ma by root 2. From here also you get e the power minus ma by root 2 when you multiply, and this constant will comes outside, and remaining you will have it this. Now if you wonder over here, this angle and this thing, okay, I'm just take this as your theta. If you realize this, these are both the same. What is e the power iota theta minus e the power negative iota theta equal to? It is 2 iota sine of theta. This is the formula, that sine of theta is equal to e the power iota theta minus e the power minus iota theta over 2 iota, right? This is the formula. So I'm using this formula and writing over here this to be equal to negative of e the power minus ma by root 2 over 4a cube 2 iota sine of ma by root 2 plus pi by 4. Shall I write the formula here? Okay. Sine of theta is equal to e the power iota theta minus e the power minus iota theta over 2 iota. Making use of this formula, I get this. Now, the third step is, first we calculate the poles, then we calculated the residue, and third step is now to calculate, okay, by using the Cauchy, now I have to apply the Cauchy's theorem. What is the Cauchy's theorem? That is the integration over the whole contour f of z dz is equal to 2 pi iota times the sum of the residues. And sum of the residues I just got right now over here. So 2 pi iota times sum of the residue, which is negative e the power negative ma over root 2. I'm sorry. Over 4a cube 2 iota sine of ma over root 2 plus pi by 4. When you multiply this 2, okay, 2, this will cancel with 4 and iota will be negative 1. And finally you get this to be equal to pi e the power negative ma over root 2 over a cube sine of ma over root 2 plus pi by 4. That's it. This contour C is split into two along the real axis and along the contour. When you apply the limits for the real axis, along the real axis, remember you have to change the function in x. So I'm having my function as e the power iota mz over z square plus a4. Just replace that with x, your real original function, right? Plus, when you integrate along the contour, along the semicircle tau, then your function will be in z, right? This is very, very important. When you are integrating along the real axis, make your function in x. When you are integrating along the contour, that is over the upper half plane for tau, then you use your terms in z. Now applying the Jordan's lemma. Before applying the Jordan's lemma, I need to understand that whatever I am having in this tau, that is 1 over z4 plus a the power 4. If this thing is tending to 0 as z tends to infinity, and if this is your meromorphic in the upper half plane, then only we can apply the Jordan's lemma. And I am looking over here that this function is having in the denominator I am having z the power 4 plus a the power 4, which is yes tending to 0 as z tends to infinity. And this is of course your meromorphic function in the upper half plane. So by Jordan's lemma, I can now write that this limit r tends to infinity on this integral tau on e the power iota mz over z the power 4 plus a the power 4 dz, this is 0 always for applying the Jordan's lemma, right? So just let r tends to infinity over here, mark this as 1, letting r tends to infinity over all, I get letting r tends to infinity in 1, we get, when r is tending to infinity, negative r will change to negative infinity and positive infinity. Cos of mx, okay, first I write e the power, yes, e the power iota mx over x the power 4 plus a the power 4 dx. The second integral is 0 and is equal to pi over a cube e the power negative ma over root 2 sine of ma over root 2 plus pi by 4. Now, equating the real parts. By using the Euler formula, this is your cos of mx plus iota sine of mx, and now I am equating the real parts, because when I equate the real part, I get cos of mx. I'm already needed in the integration. I need cos of mx, that's why I'm equating the real parts. If there is sine of mx, then I will equate the imaginary part, right? So e the power iota mx is cos of mx plus iota sine of mx. So just focus on the real part. You will get minus infinity to infinity cos of mx over x the power 4 plus a the power 4 dx is equal to, okay, in the right hand side it is already a real part, there is no iota. So this is equal to pi over a cube e the power negative ma over root 2 sine of ma over root 2 plus pi by 4. Now because denominator is positive, numerator is also positive, this is your even function. Cos of mx over x the power 4 plus a the power 4 is your even function. So I'm using the another property. This negative infinity to positive infinity will change to 0 to infinity twice. So this is cos of mx over x the power 4 plus a the power 4 dx is equal to, just write whole thing again. And taking this 2 to the other side, can I write, I'm taking this 2 to the other side, and I got pi over 2a cube e the power minus ma over root 2 sine of ma over root 2 plus pi by 4. Alright. So this, just mark this as 2. Finally we get a result. Alright, now the second part is we have to deduce, right? We have to deduce another result. Okay, for that just differentiate this whole 2 with respect to m. So differentiating 2 with respect to m, we get, alright, differentiate this, we get cos of mx is sine, what is the differentiation of this? It is sine of mx into, with respect to m you have to derivate. So this is x sine of mx with negative sign. So this is negative 0 to infinity x cos of mx. With respect to m you have to derivate. Do not confuse. Dx is equal to pi over 2a cube e the power negative ma over root 2. Alright. Now I'm having here sine of ma over root 2 plus pi by 4. What is the differentiation for this is? Cos of ma by root 2 plus pi by 4 and multiplying with a over root 2. Right? So first function, take this as your first function and this as your second function, right? So first function, differentiation of second plus second function, differentiation of first. So when you differentiate this, this is cos of ma over root 2 plus pi by 4 into a over root 2. Then when you differentiate the second one, you will get negative e the power minus ma over root 2 a over root 2 sine of ma over root 2 plus pi by 4. Now this negative sign will be cancelled out with the other one. And this is 0 to infinity. Okay, this is your sign. When you differentiate cos, you will get your sign. Here I am having cos of mx, so when I differentiate this, I will get negative x sine of mx. And here I am having sine, so I got the cos over here, right? Okay, this is x sine of mx over x to the power 4 plus a to the power 4 dx is equal to pi over 2a square. This a will be cancelled out with this and the power will remain 2 here in the denominator. E to the power negative ma over root 2. And this is your negative of sine. So I am writing this term first and cancel this negative with this negative, right? So I am having here 1 by root 2. I am writing the second term first. Sine of ma over root 2 plus pi by 4. And then when I write the first term, I should put the negative sign over here because I am having this negative over here. If you multiply whole thing with negative sign, you get here positive, and here also you get positive, and the first term will become negative. So I'm writing this sign negative over here. 1 by root 2 cos of ma by root 2 plus pi by 4. I hope it's clear to you. So this is pi over 2a square e to the power negative ma over root 2, and this is sine of ma over root 2 plus pi by 4. Can I write 1 by root 2 as cos of pi by 4? Yes, because I need to apply the formula. I have to cover up this formula. So this is negative of cos of ma over root 2 plus pi by 4, and instead of 1 by root 2, I am writing sine of pi by 4. Now just look here, this is sine of a cos b minus cos a sine b. This is sine of a minus b. So this is pi over 2a square e to the power minus ma over root 2 sine of a, that is ma over root 2 plus pi by 4 minus this b minus pi by 4. Just apply sin a minus b formula. So these two cancel. So I get my final result that this deduction with I have to deduce that. So this is equal to pi over 2a square e to the power negative ma by root 2. So this only I need to prove. Right, so we got finally our ma by root 2 over here, hence the result. Thank you for watching this video. So in the next video we will do some more questions like this. Thank you. Alright, good day.